Hi. So this continues our discussion of pressure and depth in a fluid. Typically, when we think about fluids, we think about liquids, but this is can also be applied to gases too, as long as we're kind of careful about it. Does say static fluid. That means a fluid that's not moving. I had previously shown the derivation of this equation that you've got down at the bottom. And I would just like to make a little edit here and say that let's not call this 2 and 1, but let's call this pressure down at the bottom and pressure at the top, which, I mean, if you notice where 1 and 2 are labeled in the figure, that's at the bottom of the volume of liquid that we're concerned about. And that's at the top of the volume of liquid we're concerned about. That way, if we've got those explicit labels, it kind of helps us to not lose track of, which one's which. So let's see about using this. It says, my question says, approximate the density of the air in this room. So obviously I'm in my office right now. If I were in the classroom, there's a whole visual demonstration here. I use something called the Physics Toolbox Suite app and the barometer on there to measure air pressure, basically at the floor of my office, and also to measure the air pressure on the surface of my desk. And, of course, if I were in the classroom, I would do the same thing there. Just use a meter stick, maybe to measure the pressure on the floor, and then to measure the pressure at a height of 1 meter above the floor. But in my office, I've used a table and the pressure at the floor and a pressure at the top of this table. That looks like a pie, but anyway, the pressure at the floor there, and I already made these measurements, was 95,826 torr. Got a bit of an issue with my my display. For whatever reason, those streaks pop up every once in a while. 95,826 torr. The pressure at the surface of the table was 95,816 torr. And I'm saying torr, it's Pascal. Sorry, that's the wrong unit of pressure. Torr is something else. Torr is pressure that's used in vacuum chambers, and that's what I happen to work with for my research, and that's why sometimes torr comes out when I really mean pascals. We notice here that as we've dropped down in height, that our pressure has increased. Well, why is that? It's because I've got more air pressing down, as the deeper down into the air I get. So the lower I get, the more air I've got above that level pressing down. Okay. So let's take and use these numbers along with the idea that P bottom equals P top plus rho GH to get an approximation for air density. The height difference between the table and the floor was 0.75 meters. And so now it's just a question of plugging in numbers and rearranging the equation. So 95,826 pascals is equal to 95,816 pascals plus rho times our constant G for gravity times our height of 0.75 meters. And when we rearrange that equation, subtract 95,816 from both sides, we end up with 10 pascals is equal to rho G H. Divide both sides by 9.8 and 0.75. We will arrive at a density number of 1.36 kilograms per meter cubed. Okay. And if you were to Google the density of air, you'll see that that's actually an acceptable value. So that's, that's within reason there. Yeah, I think this is kind of cool that we can, actually figure out the density of air just from a, an app on a cell phone and a meter stick. All right, that does it for this one.